Yeah. Welcome to lecture 2. Firstly, let me show you something. So here is our calendar for the spring semester of 2024. So you see, so for next week is February 2nd. Number 4 week, February 9. But according to the calendar, that's Chinese New Year Eve, which means after 2 p.m. we don't have class. So the class for here is canceled. Okay. We don't have class the week after next week. Okay. Just want to be clear. Okay. Yeah. Okay. Thanks for coming. So today, we study some models of the transformer. So we assume you already know the rough idea of transformer because that's neural network and deep learning too. You should have learned the transformer in the neural network and deep learning 1. So for this course, we study BERT first. We review the techniques of BERT. So later in this course, we know GPT is more important. GPT, Llama, something like Stable Diffusion, we have more information. That's a starting point for transformer. So that's today's lecture. Firstly, let me give you a brief review on transformers. Okay. So here is the Twitter from a famous AI expert. So if you want to become an expert in deep learning, it's largely about the empirical study, right? Because it's non-convex optimization. We cannot prove the convergence, so we need to do lots of experiments. So how can we pick the best thing to learn? So firstly, probably you can play with the open source machine learning library like PyTorch. Firstly, probably you can play with the open source machine learning library like PyTorch. And second, you can try some simple convolutional neural networks on the image data. And you also should learn transformers. Oh yeah. Yeah. So actually now all the attention of deep learning is now allocated. So here the good transformer is based on using the popular technique for today's AI. So in the last 5 years, I think the transformer have become the default of the most popular choice in AI models. So now the most popular approach is firstly to train the model on a big data set, and then we compute or SFT the model on some task. That's a very popular. It was used in BERT. So transformer actually they use like the self-attention based architecture. Let me review later. So why transformer is so popular? Because you give transformer more data, you make the model larger, you get better performance. It's very easy to scale. Right? Larger data set, larger model, get a better accuracy. Your model is better. That's why it's so easy to scale and people love it. So even today you grow the data set very large or the model very large, we can still see a growing performance. By the way, do you know how many parameters that GPT has? Do you know how many parameters?
1,000 billion. 1,000 billion. More than one.
Yes. More than it's going to some verified information. So it has 1.7 trillion parameters. Yeah. 1,700 billion. By the way, do you know like the model like Llama or Llama 2, how many tokens model needs to learn? Like Llama or the you know how many? So the number of tokens is number of words. And do you remember how many tokens?
2 trillion.
I can speak about it.
They use about 2 trillion tokens to pre-train the model.
Okay, yeah. 2 trillion. Yeah. And 2 times 10 to the power of the power. 2 trillion tokens, which means they needed to learn 2 trillion words. So now today it's really crazy. More than data set is so hard. Yeah, so I think the popular form model is the herd GPT-3. Second, let's study the first related thing. And also why transformer is so why it's so important, because transformer is very friendly. Also transformer is very friendly to modern hardware like CPUs. Okay, so before I explain so why it's friendly to modern hardware, let's review the rough idea of the transformers. So here we have 2 blocks. So the first block is RFM, LSTM, for example. So the second block is sub retention layer, which is the kernel part of the transformer. So I hope you learned ARM before. So for ARM, we know the input is a sequence of tokens, right? A1, A2, A3, A4. So each A here is a token or vector. So the output of RN is B1, B2, B3 for this example. So B1, B2, B3, B4, they are also token vector or word. So for RN, we know we firstly compute B1, and then we compute B2, then B3, and then B4. Sequentially, one by one. So that's basically a sequence to sequence function. That's a sequence to sequence function. So now for transformer, so the rough idea of transformer is anything you can process with RN, you can replace data with transformer. Any application app you can use RN, you can replace the same application by transformer. The difference here is we can compute B1, B2, B3, B4 concurrently in parallel. So for RN, so here we compute them one by one. But for dark retention, we compute the B1, B2, B3 concurrently all together. That's the difference between RN and the performance. This is a rough idea. Let me give you one information for the R. So why this is important? Because now Windows modern architecture like GPU, CPU or CPU, they are parallel computers. So for GPU, we know if you like, you can check the actual the architecture of the GPU. I think there is some video on GPU. You can check how GPU works. There are many. Here is the work with demo.
I introduced you to Leonardo. Paint a picture for you guys. All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen, Leonardo. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes within which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration in
10, 9, 8,
7, 6, 5, 3, 2, 1.
ladies and gentlemen, science class is now over. Thank you.
Here is the news. That's the way how we use. I like you can check the video later. Longer, better video. Yeah, you. So today we use the GPU to train AI models. So we wanted to make a full use of the computing power of GPU. How can I do that? We needed to run the very high parallelism from the algorithm to take advantage of the thousands of threads at the same time. So transformer or attention is the good candidate for maximizing the performance of. Actually, the video in the video there is a mistake. So today, I think that even for CPU, they have multi-cores. So CPU is also doing parallel computing. CPU also have multiple threads. So the video they show us the demo of CPU. I assume they mean one CPU or one core. We know even in the cell phone, your cell phone you have multiple cores, right? Like in your laptop, you also have multiple cores and different threads or indeed SIMD. So you also have parallel computing in CPU. And like you can also learn TPU. Basically, they convert everything to matrix multiplication. They addition the matrix multiplication into different blocks, compute the different blocks together. And it's also parallel computing. So that's why this is very important. We can compute the B1, B2, B3, B4 in parallel. In this way, we can take advantage of the computational power. Okay, so here is the figure of the father of ChatGPT, Ilya, who is a chief scientist of OpenAI. So there is this figure. So even in 2021, we can see transformers are very important. So here, according to Ilya, transformers are kind of used. So that's why it's so important, because we need a high power laser from algorithm and transformer and give us our high power laser. That's why transformers can take off. So let me now give you a brief introduction of star attention. So here there are some notations. X1, X2, X3, X4, they are the input tokens. Like I'm eating burger. Like I am eating burger. Okay. And then we normally use something for embedding to just do a matrix vector multiplication. So assume that our embedding process the input data and A1, A2, A1, A2, A3. So we can assume A1, A3, A4 they are in the data, but it's just embedding. And then now in the server attention for each token, we want to compute a query, key, and also a value. So here a query is, we want to use this query to match others. So the key is to be matched. A value is the information, the real information of each token. So here we want to build a relationship between any of input token. Right? We want to build a relationship between 1 and 3, between 2 and 4, between 1 and 4, between 1 and 1. So we need to have a query to connect the key of another token. Uses my query and your key. We can build a relationship. Okay. So that's essentially transformer.
How do you ensure each word is mapped to the same length vector?
Oh yeah. So if they are not the same length, we can process. We need to make sure x1, x2, x3, x4 they have the same shape or dimension.
What's the usual method to process this word?
Yeah. So normally even before the training, we need to clean the data. So for example, at different tokens they have different lengths, we cannot do a computation, right? Clean the data.
Is that done using a ML model or a more traditional method?
I think it's nothing to do with machine learning, but you can also use machine learning, right? Yeah, without machine learning. Yeah. So the probably the naive way, straightforward way, just padding. The paddle is 0. Yeah,
So what are some common types that people use to translate actual words into the tokens? Well, not tokens. They translate the tokens into embed.
So here actually the embedding decimation modification. That's a very easy. It's also the most popular. I think that you can maybe you can try different ways, but the idea is yeah, please.
When we convert the word into a token, and when the token is a vector, multi-dimensional vector, some of the tokenization are converting to vectors, right? So if we are having query, key, and vector for one token, or is it for different values of the vector. So q1 will be different, q2 will be different for as per the vector for one person. If I'm saying I am eating a burger, so I will be translated into a vector which is having multiple numbers inside. So how can I decide if q, k, and p is for particular vector or it is for particular the whole token?
Yeah, so for here, actually, so each token corresponding to each equal vector. Okay. Yeah, probably I can give you more information next time. Okay. So so here we want to build a relationship between any of the tokens or two like x. So x1, x2, x3, x4. They are our inputs, right? A1, A2, A3, A4. So for here, actually, they are sitting right here. So how can we build a relationship with them from 1 to 2 or 1 to 3? So here I mean 1, 2, 3, 4. How can I build a relationship? So we actually just do a dot product between Q and K, between my query and your. So by the way, what's the dimension or the shape of alpha 1 I? So let's assume Q is V by 1 vector. K is also V by 1 vector. So what's the shape of this one? Yeah, just one, right? Take dot product. So now we can have a scalar to represent the strength of the relationship between I and the 1, right? Between their relationship. For each pair, we can have this scalar to represent the strength. That's I think very straightforward. Right? So we can just firstly alpha 1 1 in the relationship, the strength of relationship between 1 and 1. And the 1 L 1 3 1 2, L 1 3 1 3, L 1 4 1 4. And now we do processing, so we just use Somax here because we wanted to convert the alpha to alpha head, like the alpha 1 1 to alpha head of 1 1 or alpha 1 3 to. Why we want to do that? Because we wanted to control the range of alpha, make an alpha head between 0 and 1. It's more stable in the computation. It's just a kind of normalization to max to normalize it, to make this number good. So actually alpha head, alpha they have the same idea or same meaning. So we just want to do a normalization, make this easy to compute or more friendly for normalization. It is max. So alpha head is like alpha head aj is still the strength between xi and aj, and also between ai and aj. Now, so we can build a relationship between any of the two input tokens. So now let's compute attention. So what's my attention here? How can I do that? So we can just use this. Firstly, how about we compute the attention from 1 to 3? So here should be alpha head A13 multiplied by V3. So because V3 is the information of X3 or the feature, so YX3 is so like but that's should have some information. We need to know the information. Like V3 is the information of X3. And also alpha hat of 1, 3 is the strength of relationship between 1 and 3. So alpha hat of 1, 3 multiplied by V3 is a tension from 1 to 3. The same thing we can also compute the tension from 1 to 1, from 1 to 2, from 1 to 3, from 1 to 4. And then we just sum them together. And that's all the tension coming from X1. That's the first output, V1. V1 is all the tension coming from X1 to everyone. And the same idea, we can compute the V2. Also, like from 2 to 4, alpha hat 2, 4 multiplied by V4 is the tension from X2 to X4. The same thing you can get from 2 to 1, 2 to 2, 2 to 3, 2 to 4. And then we sum them together, get all the tensions coming from X2. Yeah. So you see here, actually we compute the V1, V2 this way. They have no data dependence. Okay? We can compute them in parallel concurrently. You can double check. So no data dependence. Okay. That's we compute the V1. That's we compute the V2. So basically, we can just load all this into the memory. We didn't change Q1, Q1, or Q2. We didn't update K or query into the computation. Otherwise, no data dependence. So that's why we can compute the V1, V2, V3, V4 concurrently at the same time. So the idea of attention is to compute the relationship between two inputs. So let me also briefly introduce the idea of multi-head attention. So that means each token has a multiple head. So maybe each token we need to gather different level of information. That's why we need to build a different level of head. So here in example, how about each token has two heads, which means we have two kinds of attention. So here we have a definition here. So each head will only can communicate within the same head. So here, how about we just have two input token here, AI and AJ. So each token has two heads, and 1 and 2. How about let's first compute the attention for head 1 for the first head. So like BI1 is the attention for the first head from all the attention coming from I, but only for the first head. Also the so here for example, the first part is 1 to 1, right? 1-to-1. So here 1-to-1, so the query should be QI1, right? So the P KI1 with 1-to-1. And also let's just follow the first half. And also 1-to-2. 1-to-2, the first one query is still QI1. And the second one is the P is AJ1. That's BI1. So if you want to compute the BI2, you can just use this one, first A2, QI2, KI2, and then QI2 to AJ. So I think the idea is very similar. You can just compute different group, different head group separately, but you can compute in parallel or concurrent. Yeah, so the same idea is that how I compute the BI2. Now a question is BI1, BI2. Do they have the same dimension or do they have the same shape? They are vectors.
Not necessarily, but they can have the same dimension. It's whatever dimension.
Yeah, very good. Yeah. So if you go back, you see here, actually the output dimension of the chip is depending on B, right? So so here actually we don't know. For example, VI1 or VI2, we hope they have the same shape, but they can also have different dimension or different shape as well. So here, how about we just assume they have the same shape. So here, they have the same shape. Now, if they have the same dimension, you can just merge them together. Just use a matrix. Yeah. So even you have 10 hat or 20 hat in output, just merge them together. That's a brief introduction or brief review for self attention. Let me give you a visualization for self attention. So here is our input sequence. Like the law will never be perfect, but its application should be just. This is what we are missing in our input. So end of sentence, also padding. You see here, they also have padding to make each sequence the same length. Here we have padding. So because for attention, we want to do the relationship between the end of the term. You see, so so the line, so for this line is very strong, which means this token has a strong relationship between this one, and this one, right? But we know 8 here represents the law, and the law with itself, the is also now has a strong relationship with the law. Let me give you maybe another example. So here you see the animal in the cross the street because it was too tired. The second sentence is different. Animal in the cross the street because it was too wide. So now, from the meaning entire, it should mean animal entire. But here it's too wide. That should be straight. Straight should be wide or narrow. So you see visualization, because now 8 means the animal, so that has a strong relation here, weak relation. So here it's different, because the street is wider, 8 means the street that they have a strong relation here. That's a visualization. We do the relation between pairs. So for multi-head attention, usually we want to get a different level of information or different level of relationship. Right? Maybe some heads they focus on local information, some heads focus on global information. For example, for this head you see it's more like a local information. This head is more like a local information. So for next part, let's study the transformer for computer vision for 2D. So today we introduce the vision transformer VIT. So before VIT, the computer vision application was dominated by CNN, convolutional neural network. So VIT was proposed in 2020 by Google. So after this work was proposed, it became very popular. Now many applications actually are built on top of vision transformer or VIT. So here is a photo from the former TestR AI director. So that's the title of VIT paper. Image was 16 by 16 words. The former for image recognition skill. So after this work, even for CV people or vision people, they started using more transformers. That's a converge for CV and NLP. Before this work, most transformer application, language application. After this work, now we can use transformer more frequently for both CV and NLP. So, so why VIT is so popular? Because VIT can help us get a very good performance, especially on very large data set for large model. And if we have a fair comparison, like with the same computing budget, with the transformer actually is cheaper than CNN. Let me explain this. So before VIT, so different researchers they have some early research, early work for using transformers in CV. Like some people they combine CNN like architecture with our engine. Others they replace convolution entirely, but they were not very successful. So they use a specialized. So now let me give you an overview for vision transformer of VIT. By the way, do you still remember the input first? So what's the input of first? The input of yeah. Okay. So I'll just show you the input of first transformer is the input of the sequence. And now we want to process the image data. Image is not a sequence, right? Image is something like a 2D information. So how can we convert the 2D image to a sequence? So here, the idea actually is very straightforward. How about we just partition the image into different patches? So for each patch, we use a linear projection to convert each patch to a token. So for here, like we partition image into 9 parts or 9 patches, and then we convert each patch to a token. Now we have 9 tokens. That's the rough idea for VIT. So the most important thing VIT actually is build a sequence of tokens. Build a sequence of tokens. So that's a kind of embedding. It's linearly embed each of them. This one is like embedding. And also we know image has position information. So like 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the 1D position information. Actually, for CNN, we also consider the 2D position information, right? But image is essentially a matrix. Like that's 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 0, 1, 2, 2, right? So the matrix information we need that kind of information. To process image data, that's why we need to have a embedding. And after we get our input data, a sequence of tokens, we can just use PERT or other controller process. That's a rough idea of the data transformer. So the key idea, key part is here. Partition image to different tokens and add data information. So now we want to do the classification application because like MishNet or for CV, we have too many classification applications. So to perform classification, we also need not actual classification token. That's actual global information. That's the second part or second trick for VIT. See, after we have the input data, now that's our model. Our input. That's exactly the same as birth. Like you can check from a paper by per paper. They just use the previous implementation. This one from a code. Okay. So now let me give you more information how the application image. Like to the image, usually let's assume the shape of this 2D image is h by w by c. So h by w is the shape of the image. Like h is 500, w is 700, 500 by 700 image. C is the number of channels in the image. So now let's firstly flatten the image. So now we want to partition this image to n parts, right? Each part is P by P by C. So that means each patch is a square P by P. So the size of each image or the shape of each patch image is P by P. We have n patches. And I think the very straightforward P by P PV is the variation of the patching. N is big W over P squared, number of patch. Also, number of patch is the sequence length, right? How many opens we have, how many pipes we have. That's into the sequence length. That was the TA number is into the sequence length of each positive three.
The latest should be 4000 lines.
Yeah. For K, right? Okay. For K. Yeah. So for ChatGPT, so input length is a number like 4K. So here in this demo, the input length is only 9 because that's a very naive demo. Usually you have the 3D CT image, 3D CT image. So the input big length can also be 500 or probably each you can give us more information about
For typical MRI or CT scanning is 256 by 256 by 256.
Okay.
So it's a pretty long thing.
Okay, yeah. 256 by 256. For example, how about the patch is 16 by 16, which means we have 16 by 16 opens is 156 opens.
But it's written.
Oh yeah.
Yeah.
So in the future, even for CD, we may have a long sequence data.
Actually, even not story on there.
Yes. Yeah. But you can set the base size as 1. And that's 1, which means just process 1 sequence operation.
So this VIT is basically for image classification or basically object detection or something that is related to images, right? In languages, there are sequences, but here we are making sequence of different patches. And if we see the tweet that you showed the first, there are two VIT models compared to each other, and there is one ResNet and one efficient map. But the difference of accuracy is very less compared to the VIT. Is it because we are creating the patches, which is 9 in total? If we increase the number of patches, the accuracy will increase or something.
Oh yeah. So you mean the slide later, right? The comparison between.
No,
Yeah,
the before one. I guess the first tweet that compares the model, the VIT models to ResNet and efficient in the first slide of VIT. Yeah, this one.
Oh yeah. Okay. You see here, I will show the result later. Yeah.
Okay.
Yeah. So yeah, I think that may depend on the patch. So here it's too complicated. We need to do more study. Okay.
Sorry, can you go to the next slide? Slide 27. Here the XP represents each patch or all the patches?
XP.
Yeah.
Okay. So here, right? Okay. Yeah. So all the patches.
All the
patches. You see. And that's all the patches. We
So
have n patches,
right, each patch would be T squared by.
P squared. Yeah.
That's why decoder is not.
Oh yeah, it's a very good question because this work was published in 2020. It's before ChatGPT.
But transformer also have.
Oh yeah, that was just a joke.
Oh.
Yeah, I think you can also use decoder for that.
What if the information you want is like lie between the packets, and you actually slice it into different packets?
So yeah, we want each patch is local information. We have another extra embedding for global information. So each patch is local information. We also have a global information package.
Yeah, but what I mean is like you have some information, but it actually lies in the boundary, and the information is split up into different packets.
Yeah, but we have a relationship and to there. We have all the information. We put everything into the transformer. Yeah, so we also do embedding here, just convert them to a in-condition item. Yeah, so here just the same idea as embedding. Okay. Let's also talk about the position embedding. So you see, that's a patch. So here, the pink box is a patch, is the image. So the purple box here is the position embedding. So 1, 2, 3, 4, 5, 6, 7, 9. So because transformer doesn't have position information, right? Any of two, they are equal to each other. Right? So I to 1, 1 to 1, 1 to 3, 1 to 4, 1 to 5, 1 to 1. They are equal. They are equal. So now for images, they are actually not equal. They have the order information, the position information. That's why we need the position information. So that's why we actually want to add the position embedding here to give the model position information. And also, we know, so there's another one, which is the T star from bird. So because we actually just use the bird like character. So bird had T stars, so here we have an X star. So you see the pink box. This one is not attached. We add this embedding manually. Why we need this one? Or why we need the star?
To extract the whole images, and then to know the global. And we may later use it to ask the concept.
Yeah, so we need something to represent the global information. But each patch just local information. And also we cannot use any patch or any token to represent the global information. But any of this one, any of them, they all only represent the local information. We need something to represent the global information. That's why we need the star. That's why we need this one.
Why can't we have scaled vision transform? Each scale can have different size of patch. Each layer can have different size of patch. You can speed those layers.
So here actually only the input layer takes the signals.
Yeah, I'm saying why don't we have different layers of vision transform? Each layer can have different outputs.
So you mean each layer has different patches. So different patch size.
Yeah.
Each layer has different patch size.
One layer of vision transformer can have 3 by 3, another layer can have 2 by 2.
So here for conformer, actually we are we are repeating the same block. So you mean after the first layer or first block, we already get the information and then just feed the information to the next layer. Yeah, so we only like we actually only one in the beginning. So also here, let me also briefly explain the difference. Yeah.
Oh, sorry, just going to the previous slide. I'm wondering if why they don't add more class tokens. Why just one class token? If you added more class tokens, then we can get different types of the global representation.
Okay, yeah, the verification, yeah. So I think so adding more is okay, I believe. So here they probably believe that's enough because the patch size because this guy has the same shape or same dimension as the patch. Probably it's enough right there. 15 by 15 or 20 by 20. So also a big difference between CNN and transformer is inductive bias. So inductive bias means we assume the image has local information, has the feature of the locality. That's why like you can review CNN convolutional networks. They use a kernel, right? Kernel process the image block by block, block pixel by block. So each block pixel would assume they are connected. That's why we build a kernel. We have local information. But here, with transformer, actually, we only have 1D position information. You see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 0, 2, 1, 2, 2. It's not 2D. It's just 1D information. So that's a big difference between yeah, CNN. You assume the image has inductive bias. It means no path to the potential information. So and also CNN, we can also use CNN and the transformer together. How can I use together? Transformer is very efficient to help us to learn, partially generated AI. But CNN is also good at the feature map. For the input data, we want to build a fast feature map of each input data. CNN can use the feature map. You can just use the kernel to scan the image, build some feature map, and each feature map is a patch, and then send a patch to the transformer. So we can use CNN to get a patch by the feature map of CNN. And then in this way, we can control the size of the patch. Do you still remember CNN? Do you remember conclusion? Just want to double check. It's very important that we review the kernel. Use the kernel to build a feature map. Which feature map is a patch here. And we can control the size of each patch by doing kernel. And then we can also increase the distance. So like a 200 by 256 by 256 image. I think this partition is by 15 by 16, the page size 15 by 15. So we have a sequence of 16 by 15. But if we use the same kernel maximum, we can get a 256 by 256. So we can move kernel pixel by pixel by pixel. And so for VIG, so in 2020, this work was published. 2020, this model was very large. So the model is so large, and it also uses a very high resolution. Training costs are very high. So the author, they did something interesting. So they pre-trained the model on the low resolution image, and then fine-tune to higher resolution. We just want to pre-train we get a more fundamental information, and we just fine-tune the model to higher resolution to reduce the computing cost. So if you have enough computing resources, probably you can just pre-train on higher resolution. That may be better. But also, they want to save computing costs to make it faster. They pre-train on the low resolution. So that's the data flow from VIG. So here, you need to pay attention to the shape here. We know the p squared by c is a shape for a patch. So here, E. So here, we also have a D, right? So N is the number of opens, right? So D is an embedding dimension, which means we wanted to convert a patch. Patch is p squared by c, p squared c by 1, and the embedding side is d by 1. So we want to convert a vector from p squared c by 1 to d by 1, right? We just need a matrix to make multiplication. So that's a matrix vector multiplication. That's also a matrix vector multiplication. And after the matrix vector multiplication, we know this one is 1 by e. That's 1 by e. That's 1 by e. That's 1 by e. We have n plus 1 by e. So this one is n plus by e. So what do you think of the shape or dimension of the what's the shape or dimension of the
n plus 1 multiplied e.
yes. But you see, that's a vector addition, right? So this one should have the same dimension as EPOS. EPOS is n plus 1 by e. That's also recoverable. That's our input data. That's our input data, a sequence of components. And then we just do a layer normalization. Firstly is a multi-head self-attention process. And then multi-layer perception. And then do layer normalization. And then we do this over and over again. That's just the data flow of the format. Yeah. Actually, before VIT, I believe there was a similar idea. We know we can replace any LHCM with transformer. So going back to RM transformer, we can also process the image. So here, for example, we use LHCM, we partition the image into different rows. So that's the first image. So here how about we have 28 steps. We partition each image 28 times. Difference is we compute each row one by one, cell by cell. The idea is the same. They're the same. I think so. Here just sequentially transformer is in parallel. Like you can check the code here. Should be very easy to display the code here. Now, let me show you different version of VIT or game transformer. So we know ResNet 50 has roughly 24 million per minute. How about the VIT? So the author gave us 3 different versions of the VIT, like 24 there, 32 there. You see that that's the 8th dimension side. That's MLP side. That's number of cats. And that's full number parameter. So VIT has more parameters than ResNet 50 at least. So now let's have a comparison between VIT and ResNet. So here that's the VIT. That's ResNet 152 layer. That's ResNet 50 layer. That's also ResNet 50 layer. So VTAB is a benchmark, just like a testing data set. So you see on different comparison, VIT and get a better output. VIT and get a bigger part results. Also, that's the overall comparison with VIT. That's VIT, that's VIT, that's VIT, that's ResNet 1. Okay. You see the accuracy higher is better. Higher is better. VIT can get the best accuracy. Also, that's computational logic. So that's TPU core days. For example, if I finish this computation, I need 2500 TPU core days. If I have 100 TPU cores, I need 25 days. You see the computational cost of VIT actually is lower. You can get they can get a higher accuracy. Also, that's another comparison. So we have a larger data set. For small data set, actual ResNet is still better. But for large data set, VIT come from behind. Beat ResNet. Okay, now the final part of today's lecture is alpha first. So let me introduce alpha first. By the way, I think alpha first is a very good example for your final project. Alpha first, the author wants to make a better version, right? You can also take a model to make it better. So why this model is not efficient? What I can do to make this model better? Alpha actually is a good example for the final project. Actually, simple. Can you make a stable diffusion better? can you make OpenAI the DALL-E 2 better? Or even can you make a Llama 2 better? So here, AlphaBird. So why should we study AlphaBird? I think the techniques AlphaBird, they are very useful. They propose some useful techniques that you can use for other models or your AI applications. Also, AlphaBird is the most cited paper in ICRR 2020. So ICRR is now probably the #1 deep learning conference. So the full name of AlphaBird is light bird for self-supervised learning of long representations. And also, when AlphaBird was published in 2020, it achieved state-of-the-art results. Here is the results. So let me briefly explain the motivation of AlphaBird. So we know BERT was published in 2018. So from 2014 to 2018, people kept growing the model and also growing the data set. So by 2020, I think we reach a saddle point, which means we increase the model. We cannot see big improvement. So that's why, because this work was published in 2020, the work was finished in 2019. I believe December 2019. So people wanted to make the model efficient, not just scaling the number of parameters. So the first question is, can we make a better model by fewer number of parameters? Can we make a better model by reducing number of parameters? Or is the smaller model can achieve even better performance? That's the key question AlphaBird also wants to ask. And also we know the model is not very hard. Also is also very high. Also training speed we now in GPT-4 we need 5,000 GPUs daily. So AlphaBird they want to build a better model with fewer number of parameters. I think maybe 10 years later or 7 years later, we need a similar idea again. Now people are very crazy after GPT-3 from 2028. People are very happy with GPT. Many people are building larger models. Maybe 5 years later or 7 years later, we need to rethink to make a model like this. Eventually, we will reach a saddle point, and we cannot grow the model. So now let me give you some notation. Let me introduce some notation we use in both AlphaBird and BERT. So here, H is the hidden size, A is the vocabulary embedding size, L is the number of encoder layer, 4H is the feed for the parallel size. H overall 64 is the number of attention. That's actually just a hyperparameter we use in BERT. We also use AlphaBird. Now, the first method of AlphaBird is they want to cut the time between the embedding size and the hidden dimension size. So we know we now have E and H base pairing. E is a vocabulary embedding size, H is the hidden size. So refer E is equal to H. We know E actually is nothing to do with H. So what's E? So E is the word piece embedding size. So we should so the word embedding is a dictionary. We should learn context in different implementation. A dictionary is nothing to do with the topic of who, right? So the embedding the dictionary should have nothing to do with a paper or report or book. The topic of paper or topic of report or topic of book. But the hidden size, hidden layer size, hidden layer embedding, we want to learn the context dependent information. And what's the topic of book? What's the idea of book? What's the logical structure of book? We want to use it. That's the hidden layer. So these two parts, they are nothing to do with each other. We need to cut the type between them. So that's why that's the first reason also want to cut the type between E and H. And also, if we want to make the model better, we need to make the H larger. If E is equal to H is larger, E is also larger, which means we have a very large embedding. Either we have given a parameter in our embedding, that's not efficient. Embedding just a dictionary, we should make it efficient, make it light. So the author, so here, how can we cut the tie between E and H? To break the tie between E and H. So we just do a matrix decomposition operation here. About without alpha first. So before alpha first, the embedding size is B by H. Right? Now we can just change it to B by E plus. So that's our embedding. And then we have another layer E by H to connect them together. So for birds, for example, the size is V by E. Now, V by H. Now the new embedding, the storage is just V by E plus V by H. Let me give you an example. For example, V is a building. V is a building. H is a 4 building. So here E can be okay. There's 1 building by 4 building. This 1 building by 4K, 4K by 4 building. So which means we can reduce the storage by a lot. That's the idea. First, factorize embedding parameterization. Also, the second technique of AlphaBert is cross-layer parameter sharing. So we know there are even before AlphaBert, we have different ways of sharing parameters. We can share the feed forward layer of the modular perception. We also share the tension layer parameter. So AlphaBert, we share everything. So here, let me show the difference. So first, they don't share parameters. Okay, you see, even the hidden size only 1K, we have 300 million parameters. And now, however, we share the parameters. Even we increase the hidden size 4K, we only have like 200 million. How about we have the same layer? So here, all 24 layer, we double the hidden size. from all to my small 16. Also, you see here the first technique, our also make a size. So even we share the parameters, don't reach a 0 point. So here, 0 point means the input output a certain layer in the same. But we are using basically we are using the same layer in. So the best thing for this choice is the input and output embedding are the same. So how about let me give you some data. Here is the horizontal axis layer I developed axis is the distance between the input embedding and output embedding. You see it's not a zero. Even for 24 layers, it's not zero. And also it's very smooth, which means this way we can also stabilize the technique. That's the second technique in AlphaBird. So the number 3 technique of AlphaBird is to have a better loss function. To build a better loss function. I hope you still remember first loss function has two parts. First is mask lumping model, and second part next sentence prediction. If you don't remember this, please check review the first paper, or you can find many videos. So we know mask lumping model loss function is very efficient. So let's just talk about NSP today. Next sentence prediction loss. So what's the meaning of next sentence prediction loss? Which means we have a bunch of data, we have positive example, the consecutive segments of sentence from the same documents. Negative examples are from different documents. Let me give you a visualization. So here is our training data. Document X is our training data, like paper or report or book. So we can find two sentences from this book, sentence 1 and sentence 2. So sentence 1, sentence 2, they are two consecutive sentences. Right? That's positive pair. That's a positive data point. How about we can just get another random document? In this random document, we have sentence 3. We also get the sentence 1 from the document 1 figure. That's a negative pair. The idea. So because they are from the same book, they also are two consecutive. That's why they are positive. That's negative. Like sentence 1. So today I got up for a party. Sentence 2. And then I went out for a restaurant for pancake. Maybe sentence 3 is Michael Jordan went to the NBA. Nothing to do with the AI. So NSP, we want to use NSP to improve the performance of downstream tasks. But later, different researchers they believe NSP is not efficient. Like XLNet, they just remove NSP. The video is not efficient. So we know we want to use ASP to do two things. The first thing is topic prediction. The second thing is coherence prediction. The topic prediction, I just give you examples. Get up earlier, right? First, that's a topic. Right? Second topic, Michael Jordan, NBA championship. That's also a different topic. Really, we hope we can use ASP to check difference between the two topics. That's very easy, right? ASP can do that. But for coherent prediction, we don't know. At least for empirical study, we don't know ASP can help us get the coherence between two sentences. That's why our authors they introduced the sequence order prediction. So what's sequence order prediction? Let me give you an idea. So the positive pair, actually, you can just find the two consecutive sentences. That's a positive pair. I finished high school and then I joined undergrad. That's a positive pair. And then I just swap the order. Then I joined the undergrad. I finished high school. That's a negative. You see, this is very hard to build. It's not random. They are the consecutive pair. We swap the order. We need to dictate the difference between positive pair and negative pair. That's the coherence. That's the idea of SOP, the sequence order prediction by Alford. So I feel like you can check the paper of Alford. They give lots of explanation why SOP is better than SP. But today, to my understanding, it's more like empirical study. Actually, we are not sure SOP is always better than SP. We don't know. It's empirical study. Okay, so yeah, we almost finished everything. So here are just some results from Alford. Clearly, they can achieve better performance, and the model is smaller. And finish the part very quickly. That's the effective of cross-layer parameter sharing. That's all shared. Shared engineering shared effect on non-shared. You see, just check average accuracy, which means we make the model much smaller, but we can still get a good performance here. So here is the comparison between Alpha and first. So Alpha use less time to get a higher accuracy. That's the overall comparison on the blue benchmark. So that's a pair apple-to-apple comparison between GPT-1 for the extranet algorithm and performance. So let me first give you a summary of VIT. So the most important thing of VIT is building a sequence of tokens by image. And then we add the position embedding. Also need X star for global information. The three parts VIT. For Alfred, I think that's a good demo or good example for a final project. So they have three techniques. We decompose the embedding layers. We also share parameters. We do the loss. You can use exactly the same thing for another model. With a better model. That's the technique Alfred. Yeah,
if you like, you can check more information from these papers. Okay.